Hi everyone, welcome to part 2 of the tutorial. In this part, I'll be talking about the LP-free framework for online resource allocation. Most of what I'll talk about is based on joint work with Vineet Goyal and Garuda Iyengar. Okay, so to give you a high-level view of what we want to look at, there are many settings in online resource allocation where any decision that the algorithm makes has some stochastic outcome. To give you an example, in the setting of online matching with stochastic rewards, if you match a customer to a resource, there's some probability that the customer actually accepts the match, and with the remaining probability, the customer rejects the match. So this is a stochastic outcome. It happens after you decide that you're going to match this customer to this resource. Things could be a bit more complicated. So I may match the customer to one resource. They may reject this match. So I try to match them to another resource and so on until the customer runs out of patience and leaves. We could also have stochasticity materializing in a very different form. So I match a customer to the resource. They accept with probability 1, but this may be a reusable resource. So the customer uses the resource for some random duration. It's like they rent it out and then bring it back to the system after this random duration. And I know this random duration once the resource comes back. So in all of these settings, the common thread is that I make a decision, a matching decision. It's followed by some kind of random outcome. So if I think about an online and offline algorithm, and I want to compare online with offline, the offline can be a high-dimensional stochastic dynamic program. So it would be hard to compare against the offline. And often the approach that we take might look something like I design or tailor a useful relaxation of the offline, often an LP relaxation. So because it's a relaxation, it might be a bit loose. So there's a question of what is the right relaxation and so on. The approach that we want to take in this tutorial is something that kind of bypasses this need to tailor a relaxation. So it's a general framework that can be used for a tight comparison between online and offline. And it subsumes the classic LP-based Primal-Dual method. So my goal will be to try to tell you about this framework and then to try to analyze the greedy algorithm. So a simple algorithm to kind of show how one can use the framework in these 3 settings. I'll tell you more about these settings as we go along. And in particular, hopefully I'll be able to cover the first and the third setting. If there's time, I'll also try to cover the setting in between. All right. Okay, so what we'll do first is actually look at the classic Primal-Dual framework. I'll do this through the lens of stochastic rewards. So I'll tell you about the stochastic rewards problem, and I'll use that setting as a running example throughout the talk. And then we'll look at the LP-free framework and look at some nice properties of this framework and then apply it. Okay. So the setting of online matching with stochastic rewards is a generalization of the classic online bipartite matching problem. So I have a set of resources offline. The set, I'll denote it by capital J, and small j or small I is some resource inside of this j. And then I have the online side of the graph, arrivals coming one by one. When an arrival comes, I'll use small t to denote the arrival, capital T is the set of all arrivals. So when an arrival comes, I see the edges incident to it. And in the stochastic rewards problem, each edge has a probability of success associated with it. So when this arrival comes, I have to match it to at most one resource. So if I match T to I, this match succeeds with probability PIT, and with probability 1 minus PIT, it fails. And this success failure is independent of everything else. Okay. So the probabilities are revealed on arrival, but the realization, success failure, is revealed after I decide that I'm going to match T to, let's say, I. Okay. So our goal in the stochastic rewards problem is to make these online matching decisions in order to maximize the expected size of the matching, where the expectation is with respect to the randomness in the success failure. And I want to find algorithms with good comparative ratio. So as Rad already talked about, comparing online with offline in the worst case sense, and the expectation here is with respect to randomness in the instance. Okay, so a question that we need to talk a bit about is what really is the offline here? So there are 2 sources of uncertainty. One is that these arrivals, the edges and their probabilities are revealed one by one. So this is completely known to the offline upfront. So offline knows the full graph in the sense it knows all the edges and their probabilities, but it does not know the realizations of reward. It does not know that if it what would happen if it picked a particular edge in the matching. So the realization of each edge is revealed to the offline after it decides that it wants to include this edge in the matching. Another way to say this is that the offline cannot anticipate rewards, and it gets one shot at matching each arrival. So offline can, however, go about matching the different arrivals in an arbitrary order. So this is just a simple illustration. Offline could say, hey, I want to match arrival T first. So I pick this edge, blue edge here, and then I, based on the outcome of this, decide what I want to do for T minus 1, and maybe I pick this edge. So it can go in a different order than the online arrival. Okay. So any questions about the setting of stochastic rewards or the kind of non-anticipative offline or opt that we are going to look at? Good. Okay. So the classic way to analyze some online algorithm for this kind of setting would be to look at some relaxation of the offline. So here is a simple LP relaxation. It's going to be loose. And we'll talk a bit more about it in a second, but the main idea in the LP relaxation is simply that I think of a fluid fractional world where when I match T to I, there's no randomness. T just consumes a fraction BIT of I. So that gives me this LP, and I can look at the dual of this LP, and by weak duality, I have that any feasible dual solution has an objective that's at least as much as the LP. The LP is an upper bound on offline. So I can use this to find compare ratio as follows. If you give me an online algorithm and I want to show that it is tau competitive at least, all I have to do is find a feasible solution for this linear system. So that certifies that using weak duality, it certifies that I have a tau competitive algorithm. One way to see this process of fitting a dual would be that, well, you give me an online algorithm, it makes some overall reward. I will distribute that reward among these dual variables, alpha t for arrivals, beta I for the resources. So I take all the reward in online, divide it in some way between these duals so that every edge is covered. So I can look at this as a covering constraint. The sum of alpha t plus this PIT beta I should cover the probability PIT up to some constant factor. Okay. So this kind of LP, it's not hard to see, is loose. So here's a simple example. I have one resource. I have a bunch of arrivals, 1 over P of them. Each has a success probability of P. Now, if I look at what the LP would get in this example, the LP will fractionally match each arrival, P fraction of it to the resource. So it ends up getting a total reward of 1. It matches up the whole resource in a fractional fluid way. Whereas if I think about any real algorithm, the algorithm will just try to match this resource to at least one of these arrivals, hopefully successfully. So I'll try to match every arrival to the resource if it's available. So what's the reward I get? It's basically 1 minus the probability that all of the matches fail, which is just this because everything is independent. So the real reward is something like 1 minus 1 over E, whereas the relaxation is the reward of 1. So naturally, if we want to try to get a tight or best possible compare ratio, we probably need to look at tighter relaxation. So we often need to think a bit hard about what kind of LP we want to use. Furthermore, we need to tailor this LP to different settings. So this LP that we looked at was just for stochastic rewards. If we look at some of the more sophisticated settings, it's sometimes not even clear if we can compare against some reasonable LP. Okay, so with that in mind, I'll now try to introduce the framework that we want to look at and then talk about some hopefully interesting things related to it. Okay. So the high-level idea in the framework is that instead of trying to set duals in a way that we cover each edge, let's relax things a bit. So I don't want to think about covering each edge. It's okay to cover just every resource. So a naive way to think about it could be that maybe I can try to show that for every resource, the reward that my online algorithm alg gets is at least some tau fraction of the reward that my offline algorithm opt gets from the same resource. So if I can show this, this is true for every resource. So in fact, I'm doing better than just showing a compare ratio. I'm saying that resource by resource, I am tau competitive. So this would be great if I could do it. And in this kind of an example where alg includes these red edges and opt includes the blue edges, this is true. because both alg and opt match I, so in fact, this tau is 1. However, it's easy to see that this idea is not really going to work. So just imagine that there was one more resource. So alg does not match I, this resource I, to anything, whereas opt chooses to match I to T. So in this case, reward from alg, a reward of alg from I is just 0. This inequality is not true. But at the same time, this is a very simple example. Like what's happening here is that, well, alg has multiple options. It could match T to I, it could match it to some other resource. So it decides to go for the other resource, right? So maybe the right thing to look at is not just the reward that alg makes from I, but also, well, if it had an alternative at T, what is the reward that it made from that? So we could potentially look at part of the reward that alg makes from I, and then part of the reward that alg makes from T. Why T? Because T is what opt matches I to. So if alg did not match T to I, it must have had a better option or a similar option. So let's look at part of the reward it got from T. So with this idea in mind, one could think of a constraint where we try to figure out whether the following inequalities can all hold. So beta I is a variable that will try to capture part of the reward of alg from I. And then the sum of alpha T, where we're summing over all the arrivals that are matched to I in opt, captures part of the reward of alg from all the arrivals where opt was matching to I, but alg may be doing something else. And then we want to compare this kind of a pseudo reward with the reward that opt makes from I. So interesting thing about this is that the right-hand side, if it's very high, so opt makes a high reward from resource I, then the left-hand side also would tend to increase because it also depends on opt. The set of arrivals matched to I in opt will become larger and larger as the right-hand side grows. Okay. One other way to look at this kind of a constraint is that I could just say, okay, instead of looking at this alpha T where I'm summing over some specific T, let me just look at alpha IT. Now I have more dual variables and I just sum over all the arrivals T. So this gives us a simpler form of the kind of constraint that we want to go towards. So I'll introduce this more formally in a bit, but this hopefully gives you some sense of how we'll end up arriving at the LP-free framework. So the goal here is that in both of these constraints, we have a way to try to cover each resource as opposed to each edge. Okay. So before I go into the notation and the formal framework, let me just pause here to see if anybody has questions about the high-level intuition. All right, good. Okay. All right. So here's some notation. So there'll only be a little bit more notation apart from this. So I'll walk over this slowly, and I'll be happy to remind you if you lose me on notation at some point. So we'll use, just again, repeating the basic notation for resources and arrival. We'll use big J and big T for the set of resources and the set of arrivals. Small j is a particular resource. In big J, I could also use small I sometimes, and small t is a particular arrival. I'll now start using ralg and ropt to denote the total revenue in alg and opt. This will be on some sample path. And I'll also use a subscript j in the R, so ropt subscript j to denote the total revenue that opt makes from resource j. So in particular, observe that ropt will just be a sum of rj opt, where I sum over all the resources. So I'll use this expectation to denote expectation with respect to the random outcome seen by opt in alg. And then two other things. I'll use this notation P, some algorithm opt or alg j, to denote the set of arrivals. So anytime you see capital T, it's the set of arrivals that are matched to j in opt or alg. In a similar fashion, capital J opt T is the set of resources that are available at T in opt or in alg. Okay, and this is all in sample path. All right, so here is the LP-free framework. This is one of the two forms. This is the simpler form, but it has more dual variables. So the LP-free framework says that, well, if I want to show that alg is at least tau competitive, then it suffices to find a feasible solution where the variables are alpha j(t) and beta j for the following linear system. So the first inequality is just saying that the sum of all the dual variables does not exceed the total revenue of alg. So this is the same as classic Primal-Dual. I have some total revenue in alg, and I want to distribute it among the dual variables. And the second part is the covering constraint. I'm covering each resource j. So for resource j, the sum of all the alpha j(t), where I sum over, so j is fixed, plus the beta j, should be at least some tau, the compare ratio that I want to target, times the optimal solutions revenue from j. Okay, so this is basically just saying I want to distribute total reward such that each resource is covered. Okay, so let me look at form 2, which brings out some of the interesting features of this framework. So in form 2, I am going to use the intuition that when I want to cover a resource, I look at reward from alg from the resource, and then the reward that opt may make from the resource. So look at all the arrivals that opt is matching to j. So I want to just sum up alpha t over those arrivals that are matched by opt. So this is really a special case of the first form that we looked at, because all I need to do to get this form is to set the alpha j(t) to be 0 whenever t is not matched to j, and set alpha j(t) to be alpha t when t is matched to j in opt. Okay. So why are we looking at this special case? Because it brings out some nice features of the framework, which is that you can define these duals in a way that both the left-hand side and the right-hand side depend on the optimal solution. Furthermore, inside of this expectation, I have this opt, and I could choose to define alpha t as a function of what the algorithm alg does. So I can also couple alg and opt together. So we'll see some demonstration of this later on, but I just wanted to kind of bring it out that we can do some of these things. And this version of the framework is particularly useful when each arrival is matched to one resource. The simpler version is more natural when an arrival t may be matched to multiple resources. Like in the setting where I match t to a resource, it fails, I match it to another resource, and so on. Okay, so if you keep this one in mind, we should be good for the most part. Let me pause here to see if anybody has any questions. All right, good. Okay, so let's see why this works. So the proof is pretty simple. I'll just focus on the first version, and the second version follows in a similar way. So let's say I have a feasible solution to the system. So why does that give me tau competitive algorithm? I just sum up all the second constraints, the constraints that are covering each resource. So when I see that there's a question, I'll answer it in just a second. So when I sum up all these constraints related to covering each resource, what I end up getting on the left-hand side is just the sum of all the duals. Look at the right-hand side. The right-hand side is sum of all the reward from each resource that opt gets. So this is just the overall reward of opt. So now I use the first inequality to get that the overall reward of alg is at least tau times the overall reward of opt. So if I can find a feasible solution to the LPB framework, then I indeed have a tau competitive algorithm. So the question is about covering constraints of the dual LP. I'll compare the two side by side in just a second. So if I don't answer your question at that point, just let me know again. Are there any questions other than that? All right, so if I find a feasible solution to the system, I'm good. Okay, so let me now compare the two side by side. So this is the classic dual just for the stochastic rewards problem, and this is the LP-free system. So here in the dual, we cover each edge. So I have this dual constraint, whereas in the LP-free, I cover each resource. So I'm not trying to look at every single edge. And this classic dual is written for a particular setting. So if I want to look at a different setting, I'll have to think hard about the dual and figure out the appropriate dual. Whereas this, really, it's a general framework in the sense that I don't have to change the constraints as I switch between settings. And hopefully I'll be able to demonstrate that when we use this to analyze algorithms later. Another thing related to the left-hand side is that this is an upper bound on opt, and the right-hand side, as we'll see, is tight. And furthermore, I can incorporate some properties of opt and also couple opt and ALG together inside of this LP-free framework. All right. Any other questions related to the two? All right. So up next, what we'll see is how the LP-free certificate arises a convex combination of dual constraints, and then talk a little bit about the tightness before applications. Okay. So to see how this LP-free constraint, covering constraint arises a convex combination of the classic dual, I'll again continue focusing on stochastic rewards. And I need one little bit piece of notation that I need to add on to what we have so far. So let's denote the probability that a particular arrival T is matched to J in opt using Q opt JT. So there's a probability that J and T are matched together in opt. All right, so this is my classic dual constraint for some edge JT. And I claim that the covering constraint in the LP-free certificate is just a convex combination of these constraints where the weight in the convex combination is precisely this probability that the edge JT is included in the optimal solution. So it's not a fixed convex combination. The way in which you take the convex combination depends on what the optimal offline solution is doing. But my claim is that if you replace each of these individual constraints with just this convex combination, you will basically end up with the covering constraint in the LP-free certificate. So there is algebra here, which I've included in case you want to go back and kind of walk through the steps. But I'm going to jump over this algebra. I'm also happy to answer it offline if you want to walk over it after we are done and we have some time. Okay, so I'm moving over the algebra, but it just shows that this convex combination is basically what the LP-free constraint looked like. Okay, so next I want to say a little bit about why the LP-free certificate is tight and what I even mean by tightness. Okay, so one can also show that ALG is at least tau competitive only if the following system has a feasible solution. So that's what I mean by tightness, that if ALG is in fact tau competitive, there will be a feasible solution to this. So the proof is easy. Let's just take these linear constraints and consider a trivial LP where the objective is to minimize just 0. So we can take the dual of this and use LP duality. So if I take the dual of this, here I'll ask you to trust me that the dual looks like this. It's a very simple dual. This xj variable is just equal to z. So let's just simplify it and we take the z out. And all we have is that we are maximizing a single variable z with some coefficients. Now, if this coefficient is negative, then I would just set z to be 0 in the optimal solution. And that means that this dual has a value of 0, so the primal must be feasible. So in other words, using duality, I have that if the total revenue of ALG is at least tau times total revenue of OP, then there must exist a feasible solution to this system. Okay. All right, so any questions about how it's a convex combination or tightness? All right, so let's jump into the application. So I'll focus on the simple greedy algorithm. My goal will be to try to take a simple algorithm so that I can hopefully demonstrate some of the details of how the framework gets used. I'll start as a warm-up with the basic setting of stochastic rewards, and then we'll see how basically the analysis of stochastic rewards goes almost without too many changes for the more general setting of matching with patients, and then see how opt and AL can be coupled together when we talk about reusable resources. All right, so before I start with stochastic rewards, here are a couple of useful observations. So first observation is that in stochastic rewards, where to remind you what happens is that if I match an arrival with a resource, with some probability, the match succeeds, I get a reward of 1 and the resource is used up, so I've graded it out. With the remaining probability, the match fails, I get no reward and the resource is available for a future rematch. So I can change or replace this binary reward 1 or 0 in stochastic rewards with just a deterministic reward of p, which is the probability of success. So random rewards can be replaced with deterministic rewards, but keep in mind that I'm not changing, there's still randomness in the overall process, because with probability p, the resource is actually used up, meaning I cannot match it again. With probability 1 minus p, the resource is not used up, and I can match it again and get another reward. Okay, all we are doing is just replacing the reward of 1 or 0 with just the same reward p everywhere. And this is fine. It preserves the total average reward by linearity of expectation. And here we are really using the fact that we are interested in non-anticipative algorithm. The algorithm does not know whether the reward will be 1 or 0 before it chooses this edge. So that's why I can just replace it with a deterministic reward p. Any questions about this observation? Good. Okay. So using observation 1, here is another simple observation. So if I want to write, let's say something like this, the total reward that opt makes from resource J, I can write it one of two ways. So let's look at the right-hand side first. So right-hand side is just, well, what is the reward that opt gets from J? It gets a reward of 1 if it actually matches J successfully. So I can think of that as just the probability that J is unavailable at the end. So capital T plus 1 is the end. Everything is done. So the probability that J is unavailable at the end is the same as the probability that J is actually matched to something in opt. This is the same as basically looking at the total reward. Now the rewards are in this deterministic fashion. So I sum up over all the arrivals that are matched to J in opt, the reward PJT that I get. And then I take expectation over this because this set is random. So these are both alternative ways of counting the total reward R opt J. Any questions about either of these two observations? Good. Okay. All right. So the greedy algorithm for stochastic rewards just does the following. At each arrival, it looks at the set of resources that are available. So this gray one is unavailable. These two are available. I'll match T to the resource that has the higher expected reward, higher probability PJT. That's the greedy algorithm. So this J-alg T, just to remind you, is the set of all resources that are available at T in alg. From those, pick the one that has the highest expected reward. All right. So how do we analyze the greedy algorithm using the LP-free framework? First step is to define the duals and then to see that they give a feasible solution. So to define the duals for stochastic rewards, I'll in fact just arbitrarily fix the sample paths in opt and alg, and I won't even couple them. So opt has its own randomness, alg has its own randomness, just independent. No need to couple anything. The coupling will become more crucial when we look at reusability. Okay. So now with the sample path fixed, let's just think about these duals on sample path, and then we can just take expectation over all of it. So that's going to just make it easy to define. So on the sample path, suppose that arrival T gets matched to I in alg. So T is matched to I get a deterministic reward PIT. I'll just split it equally, half and half, between alpha T and beta I. So alpha T will be half of PIT, and beta I will increase by adding half of PIT to it, because I may be matched multiple times. Everything that's uninitialized is just 0. So each time alg matches something, split the reward PIT into two equal parts between alpha and beta. That's the simple setting. As you saw in Raj's part, you need to think about the splitting more carefully, but I'm analyzing greedy algorithm, so that part becomes easy for greedy. Okay. So something to observe quickly is that one of the constraints of the LP-free framework is easily satisfied, which is that the sum of the duals, in fact, here is exactly equal to the total reward of alg. Because each time I'll make something, I just split it into two parts. So when I sum everything up, I have just summed up the total reward of alg. So this part is easy. Let's look at the interesting part. Okay, so the key thing that we need to actually look at the interesting constraint, the covering constraint, is just this simple property, which actually comes from the fact that we have a greedy algorithm. So to understand this, let's look at again some arrival T. Let's say T is matched to I in alg, but maybe it's matched to some J in opt, different from I. Okay, so we have set alpha T to be half of PIT. Now we are looking at a greedy algorithm. So it's going to pick the edge out of the set of available edges that has the highest reward. So that means that this PIT is at least as much as the alternative J, if J is available. Right? So if J is one of the available candidates in alg at T, then PIT exceeds PJT. That's what this first inequality is saying. Another way to think of it would be that, well, greedy will do at least as well as what you might do if you were to just copy opt. If you were copying opt, you wouldn't do better than greedy at time T. Okay, So the second inequality over here is just saying that, well, I can replace this indicator that is 1 if j is available at t with the indicator that is 1 if j is available at the end of the algorithm, because j might get used in between. So this is a further lower bound. So this says that, well, if j was available at the very end, then at time t, alg had the option of matching to j. But if it did not match to j, then whatever it matched to should have probability higher than pjt. That's what this overall inequality says. Okay, good. So now using this, we look at the second style, because here of the LP free framework, where we sum up alpha t over all arrivals that are matched to opt, because here we are matching each arrival to just one resource. This will be the natural framework to use. When I sum this up, I'll just use this inequality to get the following lower bound. I have a half, I have this indicator where this capital T plus 1 does not depend on the arrival small t. That's why we looked at the lower bound to make this term come out of the sum. And then we are just summing over all arrivals that are matched to opt, the reward that we get, PJT. So now this is nice in the sense that if alg does not match a particular resource J successfully, then I am doing quite well, because I'm already getting half of the reward of opt, right? So I am moving towards getting a half compare ratio. I'm in trouble if alg actually does end up matching J to something, because if that happens, then this indicator is 0. But we have the beta term to take care of that. So the beta term is just half of the total reward that alg gets. That's the beta term. And these two things are complementary. We'll see it formally in a second, but intuitively they're complementary, because the first term is high if alg never matches J. The second term is going to be high if alg is aggressively trying to match J. Okay. Let's take expectation over all of this. So when I take expectation over all of this, alg and opt, I have independent randomness. So this indicator just becomes the probability that J is available at the end. And this sum is just the expected reward that opt makes from J. And then here, this sum is just the probability that J is not available at the end, because this is the probability that alg actually successfully matches J, the reward that alg gets from J. So I'm writing these things as probabilities because notice something here. These two probabilities are going to sum up to 1. So that'll give us the proof. So the next step is just noticing that the overall reward of opt is at most 1, because here I'm just looking at simple rewards where I successfully match the resource or I don't. So I take this R opt outside, and then the sum of these two probabilities is just equal to 1. All right, so let me pause here. Are there any questions related to the stochastic reward setting? I'm more than happy to backtrack. So please let me know if I went over too fast on anything. I'll pause here for a little bit longer in case somebody comes up with a question after thinking about it. All right. So next, I want to look at, I have enough time, so I'll look at the two remaining applications. Before I look at the second application, which is matching with patients, let me make an observation that'll be useful over there. So we set for the stochastic reward setting alpha t to be equal to half of the reward that alg gets because it matches t to I. But in the analysis, what we really used was a lower bound on it. In particular, we used this lower bound where we looked at what T was matched to by opt. So T matched J to opt. So it would have sufficed if we had set alpha T to be just half of PJT if J was actually available at alg. So saying it differently, instead of looking at half of the reward that alg gets at T, I could have looked at half of the reward that I would get if alg had tried to copy T. Right? And this suffices because greedy algorithm will do better than just copying opt. Okay, so I could have said duals to summarize as if I was just looking at what happens if alg copied opt and then get half of that reward. That would have worked. All right. So with that, let's jump into the next setting, matching with patients. So matching with patients is a generalization of stochastic rewards, where when you get an arrival, you get these probabilities. You don't just have to match this T to one resource, but you may get multiple chances. This arrival is patient. Um, so it could be that in this example, arrival is patient enough to stick around for three matches. So you get three chances to try to match it successfully. So I match T to this resource one, it succeeds with probability P1, independent of everything else. If that fails, I try to match T to two. If that fails also, I try to then match T to three. So if I want to think about, for example, what is the probability that T successfully gets matched to resource three, that'll be P3, the probability of success, times the probability that the first two matches both fail. Okay. So what does opt look like for this? So in the literature, people have looked at different kinds of opt. I look at the strongest version of it because our analysis goes through for this. So opt knows all the edges and probabilities. It does not know the realizations of any reward. They are revealed after the match is made. And opt can probe edges in arbitrary order. So to take an example, opt could say, okay, I want to try to match T minus one to this resource. And then based on what happens, maybe the match fails. It decides, okay, wait a second, let me first then go to T and try to match it to this resource. And if that fails, okay, I'll come back to T minus one and then try to match it to this resource. So it can probe edges in arbitrary order, and it does not have to stick to one arrival and probe all its edges before jumping to the next one. So it can figure out an adaptive order to probe the different edges, but it is limited by the patience of these arrivals in terms of how many edges it can probe. Okay. Any questions about the setting of matching with patients? All right, so the greedy algorithm for this will try to find the best sequence of resources that it should try to match to T. There could be many different complications here in the sense that I could have some constraints on what kind of sequence I pick and so on and so forth. But nonetheless, if I search over this large space and I manage to find some sequence sigma, the overall probability that I get some reward from matching T to the resources given by sigma is just 1 minus the probability that all of the matches fail. So that's the overall probability that at least one of the match in the sequence sigma succeeds. And the greedy algorithm tries to maximize this. It could be subject to some constraints on what kinds of sequences are permissible. And that can lead to some complications in how the LP relaxations are set up, but we will be able to bypass all of that. All right. So now that the arrival may be matched to multiple resources, it will be a bit more natural to use alpha ITs. So let's make a first attempt at dual fitting. This one will fail, but we'll then fix it with some small change. So in the first attempt, again, we are going to think of arbitrary sample paths in opt and alg, and the sample paths are independent. And then when we look at a particular variable T, I'll use this notation T alg IT to denote the probability that I is the one that T successfully matches to in some algorithm alg. It could also be opt. So this is just in this small example, PIT that the match succeeds times 1 minus PKT that the first match to K fails. So this resource is not part of the sequence that T is matched to, then this probability is just 0. Okay. So I'll set alpha IT to simply be half of the probability that T gets successfully matched to I in alg. Assuming that T is the only arrival and I'm just matching T one by one, this is the probability that I is the one that T picks. So I'll set it to half of that. Natural extension of what we did in stochastic rewards. But here, this won't work. This is not a good idea because this probability may be very small. Greedy does not guarantee that this quantity will be high because what greedy is doing is taking the best overall action, the best sequence. So greedy guarantees that if I look at the net sum of these EJTs over all J that are available, that is at least as much as looking at the sum of the opt JT. So greedy guarantees that alg will take an action that's overall better than what opt would do at T. Note that ALG would do better at each individual resource at T. Okay. So as a result, this can actually be pretty small. So here's where I'll use the observation that I could have set the duals for stochastic rewards to be half of what would happen if ALG tried to copy opt. So if ALG tried to copy opt, then I would have gotten T opt IT, and this is if I is actually available at T in ALG. If I is not available in ALG, I get nothing. Okay, so why is this fine? So looking at it again, if I set it this way and I sum up all the alpha ITs over all I at a specific T, then this total reward that I'm getting here is going to be less than what greedy would get. Greedy would get the best possible reward at T. So that's going to be an upper bound on what I'm going to get by setting it this way. Okay. Any questions about this? This is really the main change. Once we do this, everything else will just follow as is without doing anything differently.
So Rajan, just one clarification question. You said opt can do any sequence of probing. So how are we defining this P I comma T here?
Good. So we'll define it in the same way, in the sense that opt is doing some sequence of probing. It may jump back and forth, but when we define P opt, we are just looking at what it does at T in isolation. And then if, for example, opt is also matching K, it goes somewhere else, but then it comes to I, then P opt IT will be defined exactly the same way. So we are really conditioning on whatever else is happening for the other resources and just focusing on taking expectation with respect to the randomness at T.
For all the probing that opt does for time T.
Yeah.
I see. Thanks.
Thank you for the question. Other questions? All right. So the beta will be set same way as before, in the sense that we'll just update the beta, add 0.5 times whatever revenue ALG makes at T from resource I. Once again, if I sum up everything, the total sum of the duals in expectation is not going to exceed the overall reward of ALG, where now I have an inequality instead of an equality because I'm setting it these alphas in a different way. Okay. So is this solution feasible? Well, we pretty much follow the same steps to see that it is. So the dual constraint now is just summing up over all T, keeping J fixed, the alpha JTs, and plus the beta J component. So once again, I have this 0.5, this indicator that is 1 if J is available in ALG at the very end. And this is just the reward of opt from T. And this part is the reward of ALG from T. So I take expectation over all of this, and then these two probabilities just sum up to 1, and I have half of the opt. So here nothing changed. Any questions about this?
I have a question, Rajan.
Go ahead.
So kind of maybe a little bit of philosophical question. So this is a kind of dual construction that the algorithm cannot actually construct the dual. It is just this assignment shows the approximate optimality of the primal and it depends on opt. Do you think there might be any application that you actually need the online algorithm to also construct the dual? Is there any advantage? Let's put it that way. Is there any advantage of the online algorithm being able to construct the dual versus an existential proof for a dual certificate, which is more or less what this is because of the PJT superscript opt part?
So let me try to rephrase your question to see if I understood it. So here, are you thinking whether we are using any features of the online algorithm at all? If that's the question, then yes, we use it over here. So to say that this inequality holds, we are using the fact that we have a greedy algorithm.
Right, but,
so
but
this
to
is not
construct the alpha IT, you need to know PIT superscript opt, but the online algorithm doesn't know that.
Mm-hmm.
But this is like some existential proof for the.
Yeah, so online algorithm will kind of know this, right? And it'll try to maximize this. So we are just taking a lower bound on that. So if it was not a greedy algorithm, but some of the water filling or perturb greedy type algorithms, Here we would have the reduced price of the online algorithm, and we would potentially say that that's an upper bound on something else that has opt in it. So that's where we kind of use that we know the online algorithm and what it is doing. I don't know if that answered.
Yeah, let me ask my question offline later.
Okay.
So Rajan, there's also a question in the chat. How can I find the schedule? Oh, sorry, that's not the question for you. Sorry. I'll send the link once more. You can continue.
All right. Okay. All right. So on to the final application, stochastic reusability. So in this setting, we match an arrival to a resource and then it becomes unavailable, but only for some random duration. So when we make a match, there'll be a random duration D sampled from some distribution DI. So this distribution can depend on the resource. And the algorithm doesn't know this duration D. So the resource will become unavailable for some time. And then after this time D, the resource will come back to the system. And then the algorithm knows that, okay, the resource has returned, I can match it again. So this is the setting of stochastic reusability, and the offline for this, in a similar way as the other offlines we looked at, knows all the probabilities, the distributions, all the edges, but it does not know realizations of usage duration. So this is revealed when the resource actually returns, and here we'll also force the offline to match arrivals one by one. So it knows the full graph, but it goes in order, matches an arrival, matches the next arrival, and so on, and it only sees when an item returned, when that actually happens. Any questions about the setting? All right, so we could also combine this with some of the other randomness, like stochastic rewards matching with patients and so on, and the analysis will keep going through. But for simplicity, I'll stick to just this simple setting of matching. Okay, so the greedy algorithm here is super simple. When an arrival comes, it has some edges. Some resource may be temporarily unavailable. They are reusable, so they may come back after some time. But nonetheless, anything that's unavailable, I ignore. And then from the ones that are available, I just match to any resource. I could have some prices on the resources, and greedy could match to the one that has higher price and so on. But I'm keeping things simple. Okay, so the setting of duals will actually still be pretty straightforward. It's when we verify the feasibility that something interesting comes up. So here we are actually going to couple opt and alg, and I'll say more about this in a bit. But for the moment, let's say you have fixed some coupled sample path in opt and alg, and then arrival T gets matched to I. So I get a reward of 1 when that happens, and I just split it evenly between beta I and alpha T. So alpha T is a half, beta I gets increased by a half. So I'm again using alpha T's because each arrival is matched to one resource instead of alpha IT. The resource here may get matched to multiple other arrivals in the future. So there's no randomness like stochastic rewards, but I may still match it to another arrival once the resource comes back. So that's why I keep increasing the beta. Okay. So now the sum of all the duals is just the overall revenue of the algorithm. And the interesting thing is in the feasibility. So once again, similar to stochastic rewards, if I look at alpha T, I have this lower bound that alpha T is at least half of whatever reward I would get from opt if J was actually available. So I would get a reward of 1 from opt if J is actually available in alg. So if I copied opt, I would do no better at time T. And beta J, if I think about what I'm doing here, I'm getting a half reward into beta J every time I match J in alg. So overall, it's just half of the total number of times I have matched J in alg. So this is just the cardinality of this set, T alg J. Okay, so when I look at all the alpha T's summed over the arrivals that are matched to opt plus the beta J, I just writing these two terms down, have this overall expression where the first part of it is the number of times J is matched in opt while being available in alg. And the second part is just the number of times J is matched in alg. Okay, so now, unlike the analysis so far, it is not going to be the case upfront that these two terms are both, one of these two terms is high. It could be that both of these two terms are actually quite small. How could this happen? Well, imagine now I have these random durations on some sample path. Alg gets stuck with a really long duration, right? I sampled a duration, a heavy tail distribution, and alg just matches J once, and then the resource just never comes back. So if that happens, this part is just 1. I'll just match the resource 1. And this part may also just be 1, because when I count this whole thing, I'm not just counting the number of times that J gets matched in opt. I'm looking at the number of times that J gets matched in opt and it's available in ALK. And it may be unavailable in ALK. So this term may also be quite small. So I could be in a scenario where both terms are small on some sample path. Okay. So one could try to say, okay, then a sample path analysis is not necessarily working. It's fine. Let's just take some expectations. But then the thing that becomes a bit challenging is that I'm taking expectations, and part of the expectations I don't understand very well, because I have to take expectations over these random points that opt matches J to T. And I don't have a good handle on that. It depends on the full instance. Okay. So the approach we can take instead is to think about a coupling. Find a way to couple what opt and ALK are doing, and then analyze it on a sample path. Okay. So the claim is that there exists a coupling of the random durations in ALK and opt such that this inequality that I care about is greater than or equal to the total number of times that J is matched in opt. So if I can show this, then notice that we are done, because if this overall quantity is at least the revenue from J in opt, then I have what I need, that the dual covers resource J. Okay, so before I give you a proof by picture of this and describe the coupling, any questions so far? All right.
So just to clarify, we're talking about 2 different couplings. In your proof, you're coupling this realized durations, right?
Yes. So I'm going to, yeah. Sorry, go ahead,
But yeah, and this coupling is, there exists a coupling of random duration. This is something that is about the decision of that, right? So that's all about just the analysis, or these are the same?
So this coupling is for the analysis, in the sense that so far the 2 applications we looked at, we just said that ALK kind of has its own independent realizations of the randomness, opt has its own. And here we are saying that in terms of the randomness in the instance, we are going to kind of share the random durations in ALK and opt in some way. If ALK is randomized and opt is randomized, that is still intrinsic to them. We are just going to worry about coupling the external randomness coming from the random durations.
I see. Okay, good. So this is still about analysis.
Yes, this is just about the analysis. Yeah.
Thanks.
Any other questions? All right. So let me just rewrite the main claim. It'll be just a small rewrite on it. The first term, I'm counting the number of arrivals that are matched to J in opt, but only the ones where J is also available in ALK. So the ones where J is not available in ALK, I won't count. The second term is just the total number of times I'm matching J in ALK, and the right-hand side is just total number of times I match J in opt. So just quickly notice that if I did not have this term, the one after the AND, which says that J should also be available in ALK, I'd be done, right? Because I'd just be counting the total number of times J is matched in opt, which is exactly the right-hand side. Okay, but the saving grace is that while I have this term, I also am counting the total number of times that J gets matched in ALK. Okay, so here's the proof by picture. So this line over here is time. So this arrow indicates that I'm moving forward in time as I go from left to right. And these dashes in different colors are some arrivals that get matched to J in opt or ALK. So the red ones get matched to J in opt. The green ones get matched to J in ALK. Okay. So let me just look at the right-hand side first. So I have a common list of random durations, and I'll describe to you how this common list gets used. But what I mean by the common list is just I take independent samples from the distribution of these durations and just make this list. So the right-hand side is just representing what opt is doing. So opt will try to match the resource to these red arrivals. So it matches to this arrival. I draw the first sample from the list. It's 2. Then it matches to this arrival. I draw the second sample from the list, it's 3, and then to the final arrival, it's 5. So in this simple instance, this T opt is just 3. I match it 3 times. Okay. So opt will just go down the list one by one. All right. So just reflecting on the fact that if I just focus on the opt on left-hand side, the red term here, just focusing on the opt, that's just a copy of what opt is doing with the blue. So let me just draw it again. These are the 3 red edges. Opt just matches to this, and then this 2, 3, and 5. Okay. Now let's bring in alg. Okay. So the first time that alg matches J is this red arrival. So when alg matches J, it will draw the first unused fresh sample that opt hasn't used from this list. Okay, so that's the way in which alg and opt will use this list. Opt just goes one by one. Alg will say, okay, opt has used 2 so far. I have not used anything. What is the first unused sample? It's the next one, it's 3. So alg will draw that. So this green edge denotes what will happen to alg. It picks the unused sample, and this returns after some time. Now, notice what will happen is that when I looked at this was a red edge. This is the edge. This is where opt matches to J. Well, now opt matches to J this arrival, but this at this arrival, the resource is unavailable in alg. So as a result, I don't really count it when I do this counting, because here I can only count whenever opt is matching J, but also that J is available in alg. J is unavailable in alg, so I don't count this particular edge. But the nice thing is that I've already counted it in some sense. I've counted this green edge in this term, which kind of covers this dashed edge that I cannot count. Okay. So next, what will alg do? So this was the first arrival alg match to, and then the next arrival is much later here. So alg will again draw the first unused sample in this list. So nobody has used this sample. It'll draw it. It turns out to be 5. And notice now that again, at this arrival, opt matches to this arrival, but J is not available in alg. So once again, I cannot count this when I count this overall thing because J is unavailable here. But once again, notice that J is unavailable, but I'm covered. So I don't get to count this dashed edge, but I've already kind of covered it with this green edge that I counted in this term. Okay. So overall, if I put the blue and the red green all together, this is what I have on the right-hand side. And this is what I have on the left-hand side. So of course, in this example, both the left and the right-hand side are 3. But the claim here is that this actually is just going to be the case always, that the left-hand side is at least as much as the right-hand side, because every time I don't count a match in opt, it is covered by some green edge. And this is kind of a unique mapping in the sense that I will not use any green edge more than once. So one can formally show this, but I'll just pause here to see if you have questions about it. All right. So this is a little bit different from the coupling that we have in one of our papers, because there we didn't use the LP3 framework. So this is just in case you have seen a different proof of this in one of my other papers. It's different because we used a different way to prove it. All right. So that covers the main part. Now, what I want to talk a bit about before concluding are some of the interesting open problems, and say also a little bit about some other applications of this framework in a variety of other settings. So one interesting open problem is to find out what the optimal compare ratio is for stochastic rewards. So all we know is that greedy is a half in general. There has been a lot of progress in special cases. So special cases meaning that you make some assumptions on the probabilities. For example, probabilities are identical and things like that, using both the LP3 framework and other techniques. So this survey, of course, there's a list of the survey on our website, list of the references on our website, and also at the end of these slides. But there's a survey that covers everything that was available on this problem until a year or two ago. Okay, I'll also make a note that this LP3 framework that we saw today subsumes an idea called the path-based formulation or path-based technique that was introduced in this paper. This paper kind of introduces a special version of the LP3 framework. Okay. So notice that because this is open, this is also an open question for matching with patients, which is a generalization of stochastic rewards. Another interesting question is, what is the optimal compare ratio, and is it better than a half when we have stochastic reusability? So for stochastic reusability, we pretty much know, we know nothing apart from a half in general. But if you look at the fractional setting, going back to part one, we have large capacity or we are matching each arrival fractionally, then we know the optimal compare ratio is 1 minus 1 over E, and this is where the LP3 framework first came from. Okay. A very interesting application, apart from these settings with stochasticity or reusability, is in matching with multi-channel traffic, where this is a setting introduced by Wahide and her co-authors, where the nuance is that some arrivals may have degree 1 edge, and this happens in volunteer matching. And what is the result of having some degree 1 arrival? So if I think about a degree 1 arrival, there is a simple decision to make. And opt and alg will both make the same decision. There's just one edge. So I match this arrival to the resource that it has an edge to. Because opt and alg are going to align, I would expect the compare ratio to improve. But these degree 1 arrivals could be kind of spread out over the entire horizon. So when they're spread out, understanding how much my compare ratio improves is somewhat challenging. And this paper, in a very fascinating way, combines a classic factor revealing technique with the LP3 certificate to get near tight guarantees. So it's combining really a classic tool with the certificate to get something powerful. Okay. There are some other settings where the framework or some version of it, something inspired by it, is also useful. One of these is two-sided matching or assortment optimization, the classic AdWords problem with unknown budgets, pricing of substitutable goods, and a very recent work by Yiding Feng and co-authors on overbooking with delayed purchases. All right. This is a list of some of the papers, and this is available on our website. I will end by just pointing you to Raj's tutorial in case you missed it and jumped in later. We will upload the slides and the video on this website eventually.